We spent the whole first semester so far talking about derivatives, and now we're going to be talking about some other things. Derivatives aren't really going away, and they'll still be important, but another concept that we're going to use is something called an antiderivative. And an antiderivative is sort of what it sounds like. It's the opposite of a derivative. And basically what you want to think about when you do antiderivatives is that you're always working backwards. The idea is I'm telling you what the derivative of something is, and you've got to figure out what the original function was. And so there's really sort of two tools that we're going to use to do that to start out. The first one, this isn't the official name, but we're going to call it the anti-power rule. And basically what we're looking at is if I tell you a derivative, let's say something like this, what we want to do is we want to think, okay, that looks like something that would have been accomplished using the power rule. So what we want to do is we want to undo the power rule. Now usually when we take a derivative with the power rule, we're going to go ahead and multiply by the power and lower the power by 1. So to do the anti-power rule, we're going to take the power and go up by 1. And instead of multiplying by the power, I actually want to do the opposite of that, which would be like dividing. But the easiest way to think of that is what you're going to do is you're just going to always take the reciprocal of the new power and put it out in front. And so x squared became x third, and then the reciprocal of 3 is 1/3. And then for this one, x to the first will become x squared, and then I'm going to multiply by 1/2 because 1/2 is the reciprocal of 2. And so that's actually going to give me a 3 in front. And then for the last one, it's sort of like there's an x to the 0 here. And so I'm going to make it x to the first and then multiply by the reciprocal of 1. So I'll still have 7. And then the last part I have to do is I have to add a constant at the end, because remember that the derivative of any constant is 0, so there could really be any kind of number here at the end, and it wouldn't matter because when I take the derivative of that number I would get 0. Now what you should always do with antiderivatives is check them. And so I'm pretty sure this is my answer. This is my antiderivative, but to verify it, I can just quickly take the derivative. So if I multiply by 3, that'd give me 1, and then that'd give me x squared. If I multiply by 2, that'd give me 6, and then x to the first. Derivative of 7x is 7. The derivative of a constant is nothing. And so if you're doing the antiderivative of something, and then you take the derivative of it, you should just end up with what you started with in the first place. The second main concept that we're going to use with antiderivatives doesn't have an official name either, but basically what we're going to do is just take a formula backwards. And when I say formula, I'm talking about things like the derivative of ln is 1 over x. The derivative of sine is cosine. The derivative of tangent is secant squared. And we have some other formulas like that. And so the idea is, if I tell you that the derivative of something, for example, was, I'm not going to make this super complicated, but let's say it was 1 over x plus secant squared. This can be a little bit tricky, but I actually don't want to use the anti-power rule. I have to just get good at this enough to recognize that, oh, wait a minute, 1 over x is the derivative of ln. And oh, hey, secant squared is the derivative of tangent. And then I always put this plus c. Every time I do an antiderivative, I put the plus c on. So this will be a little bit of a tricky thing. It's going to take some practice. But, you know, another example of this would be if I gave you something like this. So basically any trig derivatives are sort of going to fall into this kind of boat. And so what I got to do is I just got to look at these one by one and say, okay, according to my rules, cosine is the derivative of sine. So sine must have been what was here originally. Secant tangent is the derivative of secant, according to my list of trig derivatives. And I know that when you do the derivative of e, you get e, so that's going to happen here, except you got to put a 1/3 out in front. Because think this through, if you're going to take the derivative of f of x, it's got to work. So the derivative of sine is cosine, the derivative of secant is secant tangent, the derivative of this, do it if you need to, it'll work out to be e to the 3x. And then we always put this plus c on the end.